Hello, my name's Kevin. I am the gatekeeper for lunch, so I'll try to keep this brief. Um, Thanks for introducing my talk. I won't repeat the title, but here it is. So a little bit of background about my research. My research focuses on optimizing the spectral efficiency of backscatter devices to minimize spectral pollution from those backscatter devices. So unlike traditional radios, backscatter devices don't require an onboard power-hungry RF amplifier or source. Instead, they rely on an external device with enough power to generate and transmit a carrier wave. The backscatter device then communicates by introducing a time-varying impedance to its antenna, and it encodes information in the modulated amplitudes and phase of the reflected signal. This modality forms the backbone of RFID, and it allows backscatter devices to achieve ultra-low power consumption at a significantly reduced complexity and energy cost. And this low cost makes backscatter devices suitable for use in a variety of emerging IoT applications, from supply chain management to environmental sensing. And improvements to backscatter technology could enable implantable medical devices that never need a battery replacement, or wearable devices that don't require daily charging. The continued adoption of ultra-low power backscatter modulators has the potential to dramatically reduce the number and mass of harmful waste batteries. Um, so recent work has included backscatter devices that use standard data formats, which makes them compatible with the billions of existing Bluetooth and Wi-Fi devices found everywhere today. So in this expanding use of backscatter, it's important to refocus our attention on spectral efficiency. Historically, backscatter devices are not frequency selective. One open problem is that a single device will modulate every signal that's incident on their antenna. This includes the desired source, but it also includes every other source present in the environment. This can lead to spectral pollution, which has the potential to interfere with other nearby communication links, especially in today's crowded 2.4 and 5.8 gigahertz ISM bands. One way to formalize the amount of modulated backscatter is to consider the differential reflection coefficient, or the delta gamma metric. This is a frequency-dependent parameter that ranges from 0 for no backscatter to 2 for the maximum. For a modulator employing a binary modulation scheme shown here, this metric can be calculated as just the difference, the magnitude of the difference in the reflection coefficients at the two impedance states. And this bottom figure is an example of this metric for a typical pin diode modulator from 0.5 to 8.5 gigahertz. So if we were using this device at 2.4 gigahertz, it's great that our metric is really high there. But if there were nearby sources at the 915 megahertz UHF band or the 5 gigahertz Wi-Fi bands, we'd be creating unwanted sidebands. Our approach to address this is to just add a filter, a bandpass filter, in line with the modulator to create a frequency selective backscatter modulator. By introducing this filter, the bandwidth of that delta gamma response can be correspondingly reduced. And in the case of an ideal BPF with perfect transmission in the passband and perfect rejection in the stopband, we've shown that it's possible to backscatter carriers within only a single channel and reject all other carriers. But in our earlier work, we considered purely electromagnetic filter structures, so things like low temperature co-fired ceramic filters or microstrip coupled resonators. But these types of filters have relatively wide bandwidths and or relatively high passband insertion losses. But thanks to advancements in miniaturized filter technologies, which rely on electromagnetic to acoustic wave conversion, surface acoustic wave and bulk acoustic wave filters are becoming increasingly available. In this work, we focus on BAW filters, which have a desirable combination of high volume manufacturing, low cost, very small size, low in-channel losses, and high out-of-channel rejection. Specifically, we use two BAW filters from Qorvo Inc. to selectively advertise in channels 37 and 38 if the QPQ 1905 is included, and in channel 39 if the 1906 is included. The rest of my talk is outlined as follows. First, I'll quickly introduce the BLE channelization plan, and then I'll give a brief overview of the design of our backscatter modulators. I'll then present some of our experimental results before concluding and proposing avenues for future work. So here is a graphical depiction of the Bluetooth low energy channelization plan, and this was designed for coexistence with Wi-Fi. I'm not going to make you count all of them here, but I promise there are 40 BLE channels. And each of these channels is 2 megahertz wide, and they're all centered at 2 megahertz intervals apart. 3 of these BLE channels are special advertising channels, and these are used for one-way beacon transmissions. Devices employ the advertising channel in an aloha manner, transmitting on a randomized low duty cycle basis to mitigate collisions, as Domenico discussed earlier. Onto our backscatter modulator design. This is our design that's just based off of an analog device's ADG918 RF switch. The switch ports are connected to either an open or a short RF load, and that presents our 2 distinct impedances to the antenna. A lattice ICE40 FPGA implements our BLE baseband logic, which sends advertising packets at 1 megabit per second per the BLE spec. It does this by digitally generating 2 FSK modulated subcarriers to represent either the 0 or the 1 bit. And in this work, we use a packet with the identifier string Alice. We use the following benchtop connectorized experimental setup to measure the reflected power spectrum of our BSM with that Alice packet. We use a signal generator to produce our carrier wave, and we use the spectrum analyzer to measure the reflected power spectrum through our directional coupler. We measure in 3 filtering scenarios of the BSM. First with no filter attached, then with the channel 37/38 filter, and finally with the channel 39 filter. And finally, we measure with the signal generator set to one of 2 center frequencies, the first to advertise packets in channel 37, the second to advertise in channel 39. So just focusing on channel 37 here, in this case, we set our signal generator to advertise in channel 37. This plot shows the envelope of the measured normalized spectrum of the BSM in those 3 filtering scenarios I mentioned. So with no filter present, that's the black curve here, we generate modulation sidebands in channel 37, but we also generate modulation sidebands at higher frequencies, including in channel 39. As soon as we add the channel 37 filter, that's the blue curve, we still produce our modulation sidebands in channel 37, although at slightly lower power due to the insertion loss of the filter. In fact, the average in-channel suppression in channel 37 due to that channel 37 filter is only about 1.385 dB. However, if we look into channel 39 along the blue curve, we produce no modulation sidebands there. Our sideband suppression ratio in channel 39, due to the channel 37 filter, exceeds 43.21 dB. And note that our measurement capabilities are limited by the dynamic range of the instrument. Finally, if we include a channel 39 filter, no modulation sidebands are produced at all. And this is because our filter stopband simply just rejects the carrier. And in this case, our sideband suppression ratio in channel 37 due to the channel 39 filter exceeds 69.71 dB. We then validated our architecture over the air in a typical office environment with our equipment placed onto 3 carts. The first cart includes our carrier source, which is again set to advertise a packet in BLE channel 37. The second cart contains the BSM that I mentioned before, featuring that RF switch with the FPGA implementing BLE baseband logic. And the third and final cart contains an unmodified iPad, which is running an off-the-shelf BLE scanner app. And we use this to measure the RSSI metric. We conducted these measurements in a bistatic configuration with our carrier source and iPad carts fixed at a distance of 3 meters. The cart carrying the BSM was then moved in 10 centimeter increments between the 2 carts, and we recorded the RSSI at each step. We also constructed a theoretical link budget to compare our measured results, and this represents the RSSI in dBm measured at the iPad. Here, the first term just represents the output power of our carrier source in dBm. The blue terms represent the gains of each of the device's antennas. GD1 and GD2 represent the 2 path losses due to the distances between the carts, and Gmod represents the the modulation factor of our backscatter modulator, and depends on whether or not a filter is included. So we conducted this procedure with the same 3 filtering scenarios: no filter, channel 37 filter, and channel 39 filter. But note that when the channel 39 filter is included, we didn't receive any advertising packets at all because of that high sideband suppression ratio I mentioned before. Basically, the packets RSSI was buried beneath the sensitivity of the iPad. However, we were able to receive packets at all distances D1 with no filter and with the channel 37 filter included, so our expected maximum range actually exceeds 3 meters. Moreover, our measured results generally followed our modeled results after multipath effects are considered. And crucially, the results suggest that including the channel selective filter doesn't drastically reduce the performance of our BSM. In fact, the RSSI is only 0.78 dB lower on average with the in-channel filter included. So to conclude, we have introduced a channel-selective BLE backscatter device architecture that's based on bulk acoustic wave channel selection filters. This device was able to achieve an unwanted channel suppression that exceeds 69.7 dB. And again, meanwhile, our results suggest that performance is only marginally degraded if an in-channel filter is included, compared to if there were no filter at all. Future work includes integrating tunable filters that would allow channel hopping among all of our BLE channels. And I think I made good time, so if you want to get to lunch, you don't have to ask me questions.